Hello guys, welcome to Engineers Academy. Do hit the subscribe button if you are here for the first time. Today we are going to start the Mechanics of Material by R.C. Hibbeler. This is the chapter 1, example number 1, and this example says that determine the resultant internal loadings acting on the cross section at C of the cantilever beam shown in this particular figure. So we are asked to find the internal loadings at this point C, and this is the cantilever beam. The cantilever beam is supported in one end and it is free at the other end, and this cantilever beam is subjected to this triangular distributed load, and we are asked to find the internal loadings at the cross section at point C, and this point C is at a distance of 3 meters from end A and at a distance of 6 meters from end B. So now whenever we are asked to solve such kind of problems, we can do this in two ways. We can either consider we can either cut the section at C and consider this side of the beam, or we can cut a cross section. We can cut the beam here and we can consider this side of the cut section. So if you guys are considering, or if you want to find the internal loadings at C by considering this right hand side of the cut section, so then in this side of the cut section we don't have any support, right? From B to C we don't have any support, like the beam is free and there is no support from B to C. So if this is the case, there is no need to find the reactions if you guys want to find the solution by considering this right side of the cut section at C. And if somehow we are restricted to find the solution by considering the cut section from A to C, what we will do is that we have to find the reaction forces. We have to find the reactions at A to solve that particular case. So I'm going to solve this problem by considering both the section, but you guys will have the choice. Whenever we are given the choice, we will try to solve the problem by considering that section where we won't have any supports. So first of all, I'm going to solve this problem for considering this BC. So now to solve this problem, or to solve any such problem, normally we have to find the reaction forces. But if you guys know the method, you guys have sufficient practice, and you guys know the fact that if we are going to consider this BC section, then there is no need to find the reaction forces at A. But since I'm going to solve this problem and I'm going to explain you how to find the solution by using both the sections, then we have to find the reactions at A. So now to find the reactions at A, what we need to do is that we need to find the reactions, we need to consider the whole beam. And for that, we have to consider this distributed load on the beam. And we have to convert this distributed load into the concentrated load. So first of all, to find the reactions, I am going to consider the whole beam. So let me draw the whole beam, or let me copy this beam. So this is our whole beam, and we have to convert this triangular distributed load into a resultant concentrated load. So let's say that the magnitude of that resultant concentrated load on the beam will be equal to the area of the distributed load. So now this distributed load is a triangular distributed load. So the area of a triangle is always equal to 1 divided by 2 times the base. So the base of this triangle is 6 plus 9. This is 9 meters. So this will be 9 meters multiplied by the height of a triangle. So this is the height, right? So you guys can see, some will say that this will be equal to 1 divided by 2. This is the base and this is the height. And some will say that this is the base, this is the height. But the formula remains the same, right? So the area of a triangle is 1 divided by 2. This is the base, then this is the height, right? So the base is, let's say, 270. 270 Newton per meter multiply by 9 meters. Now you guys can see meter will cancel out. So this will be equal to 1 divided by 2 into 270 multiplied by 9. So 1 divided by 2 is 0.5 multiply 270 multiply by 9. This gives us 1215, right? So 1215 Newton. So what you guys need to do is that you guys need to replace this distributed load with this concentrated load. Now the second question is that where must this resultant force be acting? So always this force will be acting at the centroid of its shape. So let's say if we are given this distributed load in the shape of a triangle, then the centroid of a triangle is at a distance of 1/3 from this base. So 1/3 from this base, or from this end it will be 2/3. So the centroid of this triangular area will be somewhere here, and this distance will be 1/3 of this length. So 1/3 of 9. So we can say that this resultant force will be acting at 1/3 of the height of a triangle, or we can say that the length of this beam, which is 9. So this is equal to 3 meters. So now we have to consider this diagram, this free body diagram. We have to draw this resultant force at a distance of 3 meters from end A. So we will have end A here. We will have that resultant concentrated load of magnitude 1215 Newton at a distance of 3 meters, and this is our point C, remember, and this is our point B. Now since we want to find reactions, this is the procedure. Consider the whole beam, convert the resultant force, convert the distributed load into the resultant force, and the point of application of that resultant force will be at the centroid, or will be passing through the centroid. So the centroid of this given shape, this given triangle, is at a distance of 1/3 from this base. So this will somewhere here will be the centroid, and the force will be passing through this centroid. So now this is the free body diagram, and at A, since this beam is fixed at A, so we will have a X reaction, we will have a Y reaction, and we will have the moment at A as well in the counterclockwise direction. So now to find the reactions, to find AX and AY, we have to apply the equilibrium conditions, right? So first we will write reactions. So to find AX, we have to apply the sum of forces along X, that must be equals to 0. So only AX is acting in the horizontal direction. That is, if let's say if this is our positive X and this is our positive Y, then only AX is acting in the positive X. So this is our positive X direction. So AX is equal to 0. Then the sum of the forces in the Y direction is equal to 0, and the upward direction is considered to be positive. So then we can say that AY minus the resultant force, which is 1215, this is equal to 0, and we can say that AY is equal to 1215 newtons. So the vertical reaction at A is equal to the resultant concentrated load of that distributed triangular load. AY is equal to 1215 Newton. Similarly, to find the sum of the moment at A, this is equal to 0 as well. So this MA is in the counterclockwise direction, so counterclockwise moment is considered to be positive, and it is a free couple moment, so this will be plus, minus that, since you guys can see this is producing the clockwise moment, so the clockwise moment is minus, and the moment will be equal to 1215 multiplied by the perpendicular distance. So the perpendicular distance of this force from that end A is this 3 meters. So we will multiply this with 3, this is equal to 0, and we can say that MA reaction moment at A will be equal to this 1215 multiplied 3, which is 3645. So 3645. So 3645 Newton meter. So now these are the support reactions at A. Now first of all, I will find the solution by considering this BC section. Now to consider this BC section, what we need to do is that we need to cut the beam at this point C. And with the beam, we also need to cut the distributed load as well. So if I cut the beam here, so we will consider this diagram then. Let me cut the beam first. So you guys will have the free body diagram like this. Let me extend this, and we will have the distributed load will look like this now. So now you guys can see that we need to find, at this end we were given the intensity of the distributed load. So the intensity of the distributed load at A is 270 Newton per meter, but this intensity is decreasing along the length. So we don't know the intensity of the distributed load at point C since we have cut this beam. So we have to find the intensity of the distributed load here. So let's say that the intensity of the distributed load at point C is, let's say, this W, or you guys can see it is, let's say, omega. So we have to find this intensity of the distributed load at point C. So how to find the intensity of this distributed load? We have to consider similar triangles. We have to consider these similar triangles. So we want to find the intensity here. So we must consider these two triangles to find the value of this W intensity at point C. So we have to consider the properties of similar triangles. So we have to consider a triangle, right angle triangle like this. So we must consider that this is 270 and somewhere here is that W, right? We want to find this W, and we know that this W is at point C, which is 3 meters from end A, and this end is end B, and this length, we know that this length is 6 meters. So we can say, by considering this big triangle and considering this small triangle, we can consider the properties of similar triangles. So we can say that the ratio of the corresponding sides, the ratio of this divided by this, will be equal to this divided by this. This is the properties of similar triangles. So this is one triangle and this is the second triangle, and both triangles are similar triangles since the angles of both triangles are the same. So we can say that W, which is the intensity of the distributed load at point C, divided by 6 meters, is equal to 270, the intensity of the distributed load at A, divided by this, which is 9 meters. So first is this big triangle, so this side divided by this side. So 270 divided by 9 will be equal to this divided by this. So considering this side divided by this side is equal to this side divided by this side. So we can say that at C, the intensity of the distributed load will be 270 divided by 9 multiplied by 6. So this is equal to, this is 270 multiplied by 6 divided by 9. This gives us 180. So 180 Newton is the intensity of the distributed load at point C when we have cut the section, when we have cut the beam at point C. So this is equal to 180 newtons. At C, we will have the shear force in the downward direction, let's say. So we will have the shear force in the downward direction, and we will have the normal force, let's say, in this direction. Let's say this is NC, this is VC, and we will have the bending moment in this direction. So let's draw VC. This will be our VC. This will be, let's say, our normal force at C, and let's say this is our bending moment at C. This is MC. Now we want to, considering section BC, we want to find the internal loadings, we want to find VC, we want to find MC, and we want to find NC. And again, considering this BC section, we have to apply the sum of the forces in the X, the sum of forces in the Y, and the sum of moment. In other words, we have to apply the equilibrium conditions. So I am going to apply the sum of forces in the X. That must be equal to 0. Towards the right is our positive X direction. Now NC, the normal force at C, or we can say that the normal internal force at C is acting towards the left, which is negative, so we will write minus NC, and there is no other force in the horizontal direction, so this must be equals to 0, or we can say NC is equal to 0. So there is no normal internal loading at C. So there is no normal force to the cross section at point C. Similarly, the sum of forces in the Y, that must be equals to 0. Towards in the upward direction is our positive Y direction. So now we can see, to apply the sum of forces at Y, we have to convert this distributed load into the concentrated load. Otherwise, we won't be able to apply this. So now what we need to do is that, again, using the same method, the resultant concentrated load, which will represent this distributed load, will be equal to the area of this triangle. So we can say that if we want to replace this triangular distributed load by a single distributed load, we have to find the area of this triangle. So we must say that the resultant concentrated load at section BC, let's say FBC, will be equal to the area of a triangle, which will be equal to 1 divided by 2. The base is 180. This base is 180, and the height is how much? So from B to C, this distance is 6 meters, right? So we must show this length. This is 6 meters. So 1 divided by 2 into 180 into 6, this is equal to 1 divided by 2 is 0.5 multiplied by 180 multiplied by 6. This is equal to 540. So 540 Newton force will replace that distributed load, and this 540 Newton force will be acting at the centroid of this small triangle now, right? So where will be the centroid? So we can say that the location of the centroid of this triangle will be 1/3 from this end, or 2/3 from this end. So 1/3 from this end will be 1/3 of 6, which is 2 meters. So we can say that to replace this triangular distributed load on this section BC, we have to draw 540 Newton force at a distance of 2 meters. So now the free body diagram will look like this. So now to find the sum of, or I will say that before going to apply these equilibrium condition, always convert the distributed load into its concentrated resultant load and find the location of that concentrated load. So then the sum of the forces in the Y will be equal to, so this VC is in the downward direction, which is in the negative Y, so we will write minus VC minus that 540 Newton force, which is acting in the downward direction, that is in the negative direction. So minus 540, this is equal to 0. So we can say that minus VC is equal to 540 Newton, or we can say that VC is equal to minus 540 Newton. So this means that the assumed direction of VC is not accurate. VC is acting in the upward direction. The sum of the moment at point C, that must be equals to 0. So we can say that MC is in the clockwise direction. Counterclockwise moment is considered to be positive. So MC, the assumed direction of MC is in the clockwise direction. So we will write minus MC. And this 540 Newton force is producing the clockwise moment about point C. So the clockwise is again negative, minus 540 into the moment arm. The perpendicular distance of this 540 Newton force from in C is 2 meters. So we will multiply this with 2, and this is equal to 0. So we can say that minus MC is equal to 540 into 2, or we can say that MC is equal to minus 540 into 2. So 540 into 2 is 1080. So MC is equal to 1080 Newton. So here we have determined all the internal loadings at point C. So VC is equal to 540 newtons, and VC is acting in the upward direction, and the bending moment at the cross section C is 1080 Newton. And we have found this solution by considering the right hand side on the cut section. We have considered the BC cut section of the beam. So this is the end of the problem. So if you want to find this VC and MC by considering this left hand side, so for that we have to consider this side of the cut section, the left hand side of the cut section. So let's consider the left hand side of the cut section. So for that we have to draw another free body diagram, and with that we will consider the distributed load on this side as well, whatever shape that distributed load will have on this side. So let me copy the distributed load on this side now. So you guys can see this will be our distributed load now. So now this is our point A. Let me write point A here, and this is our point C. And now at point A we have determined the reaction forces, so we will show the reaction forces. So NC is equal to 0, but we can show that AX is equal to 0, but we must show AY and MA. So AY is, we have AY here that we have determined. So AY magnitude is 1215, and we have MA in the counterclockwise direction. We have MA, and let's say that this is MA, which was 3645, right? So 3645 Newton meter. 3645 Newton meter. Let me write it. 3645 Newton meter. And we have to find VC. So let's say that the internal loadings at C is now, here we have NC, and here we have VC, and here we have the moment, the internal moment at C, the bending moment at C. So now we have to find this NC, VC, and this MC. Now before going to apply the equilibrium condition, we must convert this distributed load into the concentrated load, and the intensity of this end of the distributed load was given in the problem, that which was 270. So we must consider this 270. So this was 270 Newton per meter, and while we have considered this cut section, we have determined the intensity of the distributed load at point C, which is 180. So we can use that W equals to 180 Newton as well. So now we can see that this distributed load can be subdivided into two shapes. So one is the rectangular shape and one is the triangular shape. So in order to convert this distributed load, we must consider two shapes, and we must find the concentrated load for the rectangular region, and we must find the concentrated load for the triangular region. So now F1 will replace the rectangular distributed load, and the magnitude of that F1 will be equal to 180, the area of a rectangular, right? The rectangle. So 180 multiplied by 3. So 180 multiplied by 3 is 540. So 540 Newton. And where this F1 will act? This F1 will act at the centroid of this rectangle. So the centroid of this rectangle will be at 3 divided by 2, right? So this will be 3 divided by 2, or we can say that the center of the rectangle, right? So the center of a rectangle will be at a distance of 1 divided by 2 of this length. So this length is 3. So this will be 1 divided by 2 into 3, which is 1.5. So this 540 Newton force is going to replace this rectangular distributed load, and this 540 Newton force will act somewhere here at a distance of 1.5 meters from point A. We will have 540 Newton force acting somewhere here, and the location of this 540 Newton force will be at a distance of 1.5 meters. And similarly, we have to replace this rectangular distributed load by its concentrated load as well. So we will say that F2 will replace that triangular concentrated load, and F2 magnitude will be equal to 1 divided by 2 the base and height of this triangle. So the base is, this is the base. So the base will be equal to this 270, this is 270, right? So 270 minus 180. So the base is 270 minus 180. We can say that this is 270 minus 180. Since the intensity of the distributed load at A is 270, and the intensity of the distributed load at point C is 180. So then this intensity will be equal to 270 minus 180. So 270 minus 180 into the height of a triangle, which is 3 meters. This is 3 meters. So multiply by 3. So this is, we can say 1 divided by 2 is 0.5 into 270 minus 180 into 3. This gives me 135. So 135 Newton. And this 135 Newton force will replace this triangular distributed load. And this 135 Newton force will now act at the centroid of this triangle. And the centroid of this triangle is at a distance of 1/3 from this side, from the base, or 1/3 from the peak, right? So from the apex. So 2/3 from the apex, and 1/3 from this end, right? So we can say that 1/3 location of F2 is 1/3 from the base, or we can say from point A, and 1/3 of this AC length. So AC length is 3 meters. So 1/3 of 3 is 1 meters. So 135 Newton force will act at a distance of 1 meters from end A. So we have to draw it here. So this will be my 135 Newton, and this distance will be 1 meter. So this is F2 and this is F1. F1 replaces the rectangular distributed load. F2 replaces the triangular distributed load. So now this is our final free body diagram, and now we have to draw all the internal loadings and the support reactions at A and at C. So now again we are going to apply the sum of the forces in the X, that must be equals to 0. Towards the right is positive direction. So now only NC is acting in the positive direction. So NC in the horizontal direction. So NC is equal to 0. There is no other force in the X direction. We have a X at A, but a X is also equals to 0. Remember that we had a force Ax. We had considered a force in the x direction at A, but that was equal to 0. So it's up to you guys if you want to if you guys want to show that Ax here. So we had Ax that was also equals to 0. So then we can say that NC, we can say that Ax was there, and then we can say that NC plus Ax is equal to 0. And since Ax is equal to 0, we can say that NC is equal to Ax is equal to 0. Similarly, we can say that the sum of the forces in the y is equal to 0. Upward direction is considered to be positive. Then we can say that this Ay is in the positive direction, and this 540 is in the negative direction, and this 135 Newton is in the negative direction, so minus 135, and this Vc is in the positive direction, so we will say plus Vc, and this must be equals to 0. And we know Ay is 1215, so we will replace this Ay by 1215. So we can say that Vc is equal to minus 1215 plus 540 and plus 135. So we can say that minus 1215 plus 540 plus 135, this gives us Vc equals to minus 540 Newton. As you guys can see here, we also got Vc equals to minus 540 Newton, and we have considered that Vc is acting in the downward direction, but it was acting in the upward direction here. And here we have considered that Vc is acting in the upward direction. So on this side, Vc is acting in the downward direction, right? So Vc is 540 Newton, and actually it is acting in the downward direction. Similarly, if we apply the sum of the moment at A, that must be equals to 0, and counterclockwise moment is considered to be positive. So now we can say that MA is plus, this MA is in the counterclockwise direction, and this 135 Newton force is producing the clockwise moment, so we will write minus 135, and the perpendicular distance of this 135 Newton force from that end A is 1 meters. So we will multiply it with moment arm 1 meter. Similarly, this 540 Newton force is going to produce the clockwise moment about point A, and its perpendicular distance from that end A is 1.5 meters. So minus 540 into 1.5, and here we have this MC in the counterclockwise direction, so I will write plus. So plus MC. This Vc is actually producing the clockwise moment as well about point A. So if you guys have considered the moment about point A, then we must consider these forces as well for finding the moment. So we want to find MC, and we see that Vc, which is actually acting in the downward direction, is going to produce the clockwise moment. So I will write minus 540 is the magnitude of Vc multiplied by the perpendicular distance of this Vc from end A, which is 3 meters. So we will multiply this with 3. So this is equal to 0. And we know MA as well. MA magnitude is 3645 Newton meter, which is the reaction moment at A. So we will write this is 3645. So now we can find MC. So MC is equal to MC plus 1080. This is equal to 0, and we can say that MC is equal to minus 1080 Newton meter. Now the assumed direction of MC is not right. MC is acting in the opposite direction. We have considered that MC is acting in this direction, but the minus sign tells us that the assumed direction is not accurate. MC is in the downward direction. So we can say that MC has a magnitude of 1080 Newton meter, and it is acting in the clockwise direction basically. And here Vc has a magnitude of 540 Newton. We have considered this in the upward direction, but this is acting in the downward direction. So you guys can see we have considered this BC section. We have considered this BC section and we got the value of VC, the magnitude of VC 540 Newton and the magnitude of MC 1080 Newton. And then we have considered this section AC and we got the same answer. So VC magnitude is again 540 and MC is 1080 Newton. And here you guys can see that VC is acting in the upward direction, since we have considered VC in the downward direction, but we got 540. So VC is equal to 540 Newton and it is acting in the upward direction. But you guys can see here that we got the same magnitude of VC, but it is acting in the downward direction. So the magnitude will remain the same, but the direction will be opposite. So on the right side, VC will be, if VC is acting in the upward direction, then on the left section VC must be acting in the downward direction. And the same case will be with MC as well. So now here on this section, on the right hand side, MC is acting in the clockwise direction. We got the positive sign, so this means that the assumed direction was accurate. So MC has a magnitude of 1080 Newton meter and it is acting in the clockwise direction. And similarly, here we got the magnitude of MC 1080 Newton meter and it is also acting in the clockwise direction. So you guys can see that MC is going to act in this direction, right? So on BC, MC was going to act like this, and on AC, MC is going to act in this direction. So you guys can see on one side this is acting like this and on the other side it is acting like this. But you guys can see the moment is in the same direction. So this is how you guys can find the internal loadings at a given point on a beam by considering either section. If you guys consider this, if you guys want to find the solution by considering this section, there is no need to find the reaction forces at A. If you guys want to find the internal loadings at C by considering this side, then this point A will come into our calculation and then we must find the internal reactions at A. So this is the solution and discussion on this example 1.1. I hope all this discussion will help you in solving such kind of problems. Do let me know if all this discussions helps. Do subscribe Engineers Academy for the solution of such more problems from Mechanics of Materials by R.C. Hibbeler.